Hello, everyone. Thank you so much for inviting me. I'm really excited and eager to be here. And I'm going to share with you a bit about reproducible computation at scale in R with targets. And I'm also going to touch on some extensions to targets that I haven't often publicly talked about in a setting like this. And hopefully that's going to be exciting for other Bayesian statisticians like myself and our Markdown enthusiasts as well. So there's some updates as well as some old news here. So a bit about the problems that we're trying to solve with targets. These are demanding reproducible analysis pipelines in R. Things like Bayesian data analysis with custom models or any of these model development frameworks. That we're talking about PK/PD analysis, pharmacokinetics, pharmacodynamics. We're talking about clinical trial simulation, statistical genomics, and also even things outside the life sciences like deep learning with Keras and Torch and tidy models. And I've even seen social network analysis and permutation testing workflows and ETL in general that can lead to a lot of computationally demanding work and a lot of cumbersome workflows that require or at least benefit from some kind of workflow manager. So in demanding statistical analysis workflows, there are overlooked realities that people don't often realize until they actually try these problems themselves. There's a perception when you have something like a large model to develop and fit, that you just code up the model all at once beforehand, and then you run it. And yeah, it may take a long time, but once it's done forever, and the workflow is straightforward, and you deliver the analysis at the very end. But the reality is that the model or code or ETL task requires ongoing development. Even at scale, it requires ongoing development. So you build something up, you code it up the first time, you run it for the first time, but then you go back and you realize that maybe you have a bug here, maybe you want to try a different prior distribution in the model, maybe you want to, maybe the data has changed in the intervening time and that needs an update. And you make frequent changes to the upstream code or data behind the workflow that you're doing. And the actual time that you spend that it takes to get results is really the time that it takes to run, that becomes the time that it takes to run something multiplied by the number of times that you change the workflow and have to then rerun the whole thing. And I'm not talking about with targets. I'm talking about sort of what happens when people when people don't use a workflow manager like this, and then it turns into this vicious cycle where you're repeating the same large workflow over and over again, making quick changes to the code that are often very easy to just type in, but because of the computation time, the results can't usually keep up. Now, I experienced this in my dissertation work, working on a large genomics model, a large Bayesian hierarchical model for a crop genomics problem. I experience it all the time at work with clinical trial simulation and Bayesian model development projects. And it takes a pipeline tool to really get at a solution that maximizes time efficiency in this way. So a little bit more about how this is working. So the mental model of a workflow is kind of like this graph that you see here. This is sort of the tidyverse workflow that's often talked about. And these steps are individual components of the computation. And in reality, you're going to go back and make changes. And if you do that, if you go back and say, change the model, it's not only that model you necessarily have to rerun, everything downstream is also impacted. The transformations of the model results, how you visualize that model, how you communicate that model, when that model changes, those artifacts also need to be refreshed. And there's this, on one extreme, you could rerun everything in response to those sorts of changes. On the other hand, you could analyze your workflow just manually and think about, okay, well, what artifacts were impacted by the code that I think I changed? And what do I need to rerun? And what can I skip for the sake of saving runtime? This process is unreliable if you try to do it manually. So we're left with a sort of false dichotomy of being efficient with our time and being thorough and reproducible, but wasting time. With a pipeline tool, you don't have to make that choice. You can let the pipeline tool figure out exactly which computations need to be rerun and which can be skipped, and you can have evidence of a reproducible workflow at the end. So both time savings and confidence that everything at the end is up to date with the upstream code and data. So a pipeline tool will construct a graph like this to connect the different artifacts of the workflow. So first you obtain some raw data, for example, and in a workflow like this, not all workflows look like this, but a lot do. So it's common to take some raw data to pre-process it somehow to get ready for analysis. And then you may fit some different models to it. You may visualize them and communicate them in a report at the end. And amid all this chaos and change and urgent deadlines and viewers and stakeholders that need to see your end results or papers to publish, it's hard to keep track of which models are up to date and which ones you need to rerun. But a pipeline tool can tell you, for example, in a case like this, that two of these models need to rerun, and one of these models can be skipped in order to save time. And so you can look at this, and the pipeline tool can look at this and make that decision. And then if you choose to run this with parallel computing, it can actually run these two components of the graph in parallel. So the time savings of skipping certain things and the parallel orchestration in a high performance computing sense are major benefits of pipeline tools in general. And there are a large number of pipeline tools. This list contains several, a little over 100 pipeline tools currently. It's a very sophisticated space. It's a very active, very vibrant space, and there are tons of great tools out there, and that do amazing things and have incredible interfaces. But most of them are designed for other languages, predominantly Python, or they're designed to be language agnostic for use either in the shell or graphically or so forth. Historically, there hasn't been a whole lot for R. I think personally, I don't know exactly why it's taken such a long time for R-focused pipeline toolkits to arise, but I suspect it's because of the interactive nature of most usages of the language. People like to live in an R session and experiment with their data interactively, and the idea of automated formal pipelines is a bit different, and it's not really it hasn't always percolated into the culture of the R community, but we're getting there. And there have been a few different iterations starting in the 20 teens of that I know of, at least, of pipeline toolkits for R. So Rich Fitzjohn, who is part of the leadership of R Open Sci, created a package called Remake around 2014, and he developed it for a couple of years and had to move on to sort of another job and other responsibilities, so wasn't maintaining it after that. And but he pioneered an incredibly useful mental model about pipeline tools in R, sort of a focus on functions and abstracting output files as R objects, and to really have a platform and a language to work with pipeline tools inside R and inside an R session, both following good programming practices and the conventions and standards of the R language specifically. When Rich decided he wasn't interested in developing Remake anymore, I kind of took these ideas and built a lot of them into the Drake package, which was the successor at the time. And what Drake tried to do was to scale up to distributed computing workloads, adding parallel computing in general, and to experiment with some interfaces, and to add things like dynamic branching and static branching that weren't, all of which were not available in Remake. But at the core, it's still the same mental model. And then Drake I learned a whole lot from Drake. I learned to be a better developer from that experience. The community has taught me an incredible amount, as Drake was accepted by the R OpenSci and R communities in general. And I learned an incredible amount. Most of those learnings a lot of those learnings I could apply directly to Drake, and a lot of those conflicted with the original design. And I created targets to be able to do dynamic branching a lot more efficiently, and to provide something a lot safer and a lot better designed and a lot more efficient and portable for users. So targets is kind of like the next generation of Drake, but it's higher quality software that has a better user experience. And a lot more extensibility, as we'll see. Some of the ways that I've extended targets and the community is extending targets just would not have been possible in Drake. And there's still an incredible amount of untapped potential. And I'll get into some of the more recent developments a bit later. So before we get into an example, I will just emphasize that for the general case, targets embraces what actually has become a less popular programming style in recent years. Functions are the building blocks of most computer languages, and the R language has roots in programming in terms of creating and modifying custom user-defined functions. The way data science has transitioned and the way that we've chosen to teach data science in R to democratize these skills as much as possible, and to bring people along that aren't necessarily trained computer scientists. We've relaxed a lot of these principles, but I think that in order to do what targets does, it needs to be able to infer clear relationships among inputs and outputs, and functions are the ideal tool for that and the ideal way to program when it comes to pipelines. Now, I realize that this is a burden for a lot of people, which is why some of the extensions to targets that I'll get to reduce the volume of custom code and reduce the burden of writing functions for everything in some very common cases. But for this example, we're going to write functions for a lot of stuff. We're going to write functions to obtain data sets and to fit models and to post-process results. So when you write a function for data analysis, it's typically going to be preparing a data set, fitting a model, or summarizing the results of a model. And the outputs, this example reflects that. So this is an example from Matt Danshow. He wrote in a 2018 RStudio AI blog post that on Keras, when Keras in R specifically was new. Highly recommend checking it out. It's incredibly informative. for people like me who were new to deep learning at the time and still new, we're going to analyze a customer churn data set that contains demographic information on various customers of a telecom company and whether they dropped out, i.e. canceled their subscriptions or stuck with the company. And so customer churn is important for businesses to learn, which customers stick with you, which customers leave. And that's what that's these deep learning models are going to try to get at. We're going to try to train the models and for the purposes of this particular workflow, maximize prediction accuracy. And how we structure this project is we're going to have, it's very much like a package, the way I'm choosing to describe this. There's a lot of flexibility in terms of how you organize your code in targets. Targets doesn't necessarily take responsibility for how you organize your extra code. The only required part is this target script file, which, and even that is a little bit configurable. But most workflows are going to have this special targets file to define the pipeline, and the other files that are referenced from targets.r are up to you. So we have one or more scripts with functions. There aren't very many functions, so I threw them all in a script, but you can divide them over multiple scripts, and likewise with the data. So these functions are going to prepare data sets split into training and test. We're going to prepare a recipes object. So the recipes package is part of Tidy Models, and it's one of the most amazing pre-processing interfaces to have been released in the R community recently. So that's how we take the Tidy data frame input that we start with and translate it into something that the Keras models can understand. And then we're going to take a model in this test model function. We are going to fit it to the pre-processed data, and we are going to report prediction accuracy. This is our required targets file. It's the linchpin that glues everything together. It loads the packages that are required to define the pipeline, any functions and global objects that you choose, and it sets options, including the packages that are required to run the pipeline that the targets are going to actually use. And here are actually the steps of the computation. So each call to the tar target function is what's called a target. It's a skippable step in the computation. Each target has a name, for example, data or recipe or model one. It has an R command. So just a little bit of R code that uses our custom functions and global objects and upstream targets to compute something. And ideally with minimal side effects, unless you're talking about files, and that R code will run and it will return a value. And that value gets stored in the variable whose name is the target name. And that data gets stored in a special data store so you can restart your R session and still have access to the completed pipeline. And what targets can do is it statically analyzes that code and discovers the relationships among those targets and expresses those relationships in a directed acyclic graph from left to right. So for example, targets figures out that we need to establish the input file first, then we read it in as data, we pre-process it, and then we fed our models. Now, how does it construct this graph? So for example, our data target depends on the function split data and file, and targets will crawl through all this code and it will notice, okay, I see the symbol split data and the symbol file. And so in this graph, I will need to draw directed edges between file and data. And if we were to show functions, which we can, we would also see a directed edge from that function to the data target. And this describes what's called the topology of this workflow, or just the shape. And this describes the execution order that the targets run. So which targets run first, which targets run last, which targets can run in parallel. And which targets respond to upstream changes. So for example, if file were to change, then that would change data. That would under most conditions, except if you do some manual configuration, that will queue an update to data. And then if data changes, that will queue an update to recipe, and the recipe will rerun, and so on and so forth. So the first time you run this, you use a function like tar make or tar make cluster MQ or tar make future for parallel computing. And a function like this will run the whole pipeline. The first time you run it, it will process the correct targets in the correct order in the graph, and it will store those results in a data store. And we can read those results from the data store using functions tar read or tar load, using the name of the target. And this is what I mean by abstracting files as R objects. So what's really going on is model 1 and model 3 are files saved in the project, but you don't need to know that for the purposes of trying to find your data. All you need to know is the target name, and you can treat it like an R object, and you can just load it whenever. And likewise for the pipeline, when you construct the pipeline, you don't need to read the data file for the sake of computing the recipe. You can trust that targets will actually load the data or make sure that it's loaded for you when the recipe is computed. So that is the first run of the pipeline. Suppose we change a target. So we change the architecture of our deep neural net for one of our models. We change the activation function of the first layer of this neural net in this case. What's going to happen is targets is going to notice. It's going to say, okay, most of our targets are still up to date in spite of everything, but because of that change to the command, one of our models is out of date. And so when we go and run the pipeline again, those up-to-date targets are skipped to save time. So if model 1 and model 2 each take an hour to compute, that's already 2 hours of time savings that you've spent, that you have now gotten back as far as time you don't have to spend waiting for results to come in. You only have to fit that third model, and and at the end of the day, you still have evidence that all of your results match the upstream code and data. Likewise, if you change a function. So this is one of the functions that defines our deep neural net. And suppose we want to tinker with some of the model hyperparameters, like the dropout rate in this dropout layer. So targets will notice. And this is one of the reasons why it's really helpful to program in terms of functions, because targets understands how functions work and how they're nested. So this is the same graph, only it shows the custom functions that you've written for the workflow. And when you change that define model function that I showed in the previous slide, what targets is noticing is the body of this function has changed, so it's out of date, which invalidates the train model function. The body of the train model function code didn't actually change, but train model references define model. So this is the function that calls another function, and targets knows what that means. And any results from train model also use define model because of the way they're nested. And so that invalidates all the outputs of train model. Likewise with test model. And so all of these models are now no longer up to date, and they rerun once you run the pipeline again. So this lends a little bit more confidence that if there actually is something to rerun, targets will detect it. Now, there are ways to fool targets. There are certain ways that you can hide changes from it, which is why it's really good practice to always check the graph before you run the pipeline. But in the majority of cases, for the majority of changes that you make in R, it does catch them, and it provides extra evidence that your output is synchronized with your input. And this is tangible evidence of reproducibility. And this is super important for large computation. People say all the time that reproducibility is synonymous with R Markdown and literate programming. I disagree with that. There is a lot more to reproducibility when it comes to high level and scalable, serious machine learning pipelines and Bayesian data analysis pipelines and genomics, where you have these computational issues to contend with, and it's a non-trivial issue to rerun everything from scratch. And the evidence that your output is synced up with your input is evidence that these results can be recreated by the code that you have on hand and the data that you have on hand right now. And so this gets directly at the concept of reproducing an analysis. And it's central to the idea of reproducibility in large projects. Okay, so that is targets, base targets. And I've talked about pipeline tools for a long time, but I've talked about targets a few different times. I believe around this time last year was the first release of targets, but there are some new extensions to targets. I designed it with hopes of extending it further and making some of this stuff easy on people. Reproducibility and high performance computing are great, but they're hard to democratize. It's hard to ask somebody to write functions for every single thing they do if they're a researcher, or, an ecologist or an economist who is primarily focused on their domain and getting results, and justifiably so. And to ask them to write what is almost equivalent to a package, to a new R package for every data analysis, that's a lot of work. And so it was a barrier to adoption for a long time in these pipeline tools that I've been involved in creating. But now we're sort of entering a new time where there are opportunities to extend targets to make these large-scale pipelines democratized and accessible to a lot more people. And that's what I'd like to share with you with the remaining time. So I'm calling this ecosystem the R Targetopia. So it's a collection of packages that extend targets, and I've written a couple, mainly Stan targets and JAGS targets, but there are a lot more that are possible in all kinds of domains that would benefit from large scale pipelines. And the central concept here is what's called a target factory. A target factory is a reusable function that creates target objects, that creates multiple targets for an entire section of the pipeline. So just as a schematic of an example, you could have a workflow that, much like in the machine learning example, establishes a file, reads in the data, and fits a model. You could create those target objects using a function that you define, and then instead of listing all those targets in the targets file of your particular pipeline, you could just call that target factory, which is defined in a package, and then you would automatically get those three targets for free. So this idea was not possible in Drake, and was not possible not nearly as easy in Drake or Remake, if it even were possible. I don't know. But targets is fundamentally designed internally and at the interface level much differently than previous pipeline tools. It's fully object oriented, and it's decentralized, which means each target is an object, and each target encapsulates most of the complexity and decision making that goes on in a pipeline. Instead of reasoning about all of that decision making at the pipeline level, like Drake did and like Remake did, targets does as much of that as possible on a target by target basis. Each target is an object that encapsulates its own behavior, generally without worrying about what the rest of the pipeline is doing, which allows you to define these target factories that separate out these different components. And you can build some really powerful things on top of it. And one example is Stan targets, which is exactly what it sounds like. It's the extension of targets for the Stan for the Stan programming language, and it uses packages command stan r and posterior by the Stan developers. I'm a huge fan of those packages, and they're using them a lot at work. And Stan targets makes it a lot easier to build pipelines on top of these packages. So a bit about Stan. Stan has been around for a long time, at least a decade now, I believe. And it's a probabilistic programming language based in C++. And it mainly fits Markov chain Monte Carlo with Hamiltonian Monte Carlo and the no U-turn sampling, which is in a lot of cases, not all cases, but in a lot of cases more efficient than Gibbs sampling. If you don't have conditional conjugacy in your Bayesian model, it's extremely flexible. So you can specify arbitrary posterior distributions by directly making modifications to the log posterior mixed in your modeling code among declarations of conventional priors like you would in JAGs or bugs. It's really powerful. And because of the fitting algorithm, like I said, it's indifferent to conjugacy or conditional conjugacy, depending on how you're depending on what you're using. And this, model specification is really powerful. But it not only does it do MCMC, it does variational inference and penalized MLE to maximize to find the mode of the posterior. So let's take a very simple Stan model. I'm working on a sort of a more practical and clinically motivated Stan model to share. I haven't gotten permission to share that with, but I will announce it when I have something. But this Stan model is it's very simple. It's just a linear regression of this variable y from our data on a covariate x, and we're estimating the slope and the intercept. And we just have a standard normal prior on each of our model coefficients. So this is the model that, and suppose, I code up this model, I write it in Stan, and before I actually use it for something serious, I want to make sure that it's giving reasonably correct answers. And there are a bunch of ways to do this in Bayesian statistics, but simulation-based calibration is one of these techniques. And there are a couple of great papers on that. I'm going to demonstrate a much simpler, perhaps more naive technique that's easier to do in Stan targets, and that catches a lot of genuine errors. Actually, that's been really useful for my colleagues and I to validate these Bayesian models. So what this pipeline is going to look at. How this pipeline is going to work is we're going to simulate thousands of independent replications of data of draws from the model's prior predictive distribution. And for each simulated data set, we're going to analyze the model with Markov chain Monte Carlo. And then we're going to calculate posterior intervals for each of our parameters from each of those analyses. And then we look at what's called coverage. So how often does this posterior interval, which is like a confidence interval, capture the true value of each parameter beta 1 and beta 2 that was used in these prior predictive simulations? So we want to recover, so we know the truth in each simulation, and we expect X% of the time for the model to recover that truth when it analyzes the data. And to the extent that it can do that is the extent that the model is well calibrated. So if we have 95% posterior intervals, which are the Bayesian equivalent of your 95% confidence intervals, we expect those intervals to cover these parameters 95% of the time if the model is implemented correctly. And so this is what we're doing. And yes, you do have to write some code yourself, which ideally is in the form of a function. But for this Stan targets workflow, you only need to write a function to simulate from the model, to create one draw from the prior predictive distribution. And if you're a practicing Bayesian statistician doing one of these workflows, simulating from the model's prior predictive distribution is one of the easiest things that at the implementation level that you're going to be able to do. With the exception of, maybe your model is using improper priors. And then this gets tricky, but if the math works out, the coding is very, very straightforward relative to the other things you have to worry about. So, and then maybe another function, which is also straightforward, to take the results, the summarized results from all your simulations and calculate coverage, which is just the number of times that your parameters from that you simulated are captured in these quantiles. Now, dot join data is a funny thing. If you create a data set with this dot join data list, then stand targets will automatically join these parameters to the summary output, so you can make comparisons between the data and the fitted model, and that's part of what makes this work. And now our targets file is very simple relative to what this usually looked like without stand targets. So a couple of changes here, a couple of differences. This is a large computation, and so we're using parallel computing here. In this case, with the multi-core backend of ClusterMQ, this tarstan MCMC rep summary is a target factory from stand targets. This is the target factory that powers that simulation workflow. And we give it the name of the model, we give it the summaries that we want, and we give it the code to simulate one instance of the data. And then there's a downstream target to invoke the calculate coverage function we defined before. Now this gives us, we only wrote what looks like two targets in this workflow, but we have that gives us an entire ensemble of targets, an entire pipeline from establishing the model to running the simulations to fitting to summarizing them. And all we need to do to run it is call tar make cluster MQ with any number of workers that is appropriate. There are various resources in targets and in cluster MQ about how to configure this stuff, how to use a scheduler that or a distributed computing system like these mentioned, and not just the local cores on your laptop. And there are various utilities for monitoring the progress of how your pipeline is doing and how close it is to finishing, that can really supplement the existing monitoring tools of your scheduler. And when we have the results, we have a nice data frame here of output. And in this data frame, there is one row for each model parameter and each simulation. And each column is a different quantity in the data set. So we have on the simulation. So we have these quantiles that are upper and lower bounds of posterior intervals. We have convergence diagnostics like this R hat, this Gelman-Rubin potential scale reduction factor, which is supposed to be close to 1 if the model is converging appropriately. We have the true values from the data, and we have some indicator variables to say which simulation rep am I on, which file am I using. And the output shows that coverage looks good according to this R hat diagnostic. There are a lot more diagnostics, and in practice, I would use multiple, like effective sample size and not just R hat. But for the purposes of this exercise, this looks pretty good. And then coverage is nominal. So 50% of the 50% credible intervals cover beta 1 and beta 2, and 95% of the 95% intervals cover those same parameters. And these only need to be systematically close to the nominal coverage of 50 and 95%. There are going to be some differences due to simulation error, but they shouldn't be systematically higher and they shouldn't be systematically lower. And this is what we're seeing looks pretty good. Now, there are a lot of resources on targets and stand targets. There's a lot of good stuff here for Bayesian statisticians who do a lot of pipeline work in R specifically. I encourage you to check this out if you're interested. Ask me questions, etc. With the time that I have left, I'm actually going to let's see. I guess I should do a time check first before I go on to my next thing that I was planning here, which I don't actually have slides for, but I think is worth sharing. Is there a need to move on to questions, or?
Well, there is a few questions already, but I think that's fine if you proceed.
Great. So I would like to share something called Target Markdown, which is another extension to targets, but is not necessarily it wasn't part of my original slides, and is compatible but not directly related to Bayesian data analysis with targets. It is I've documented it. It's in development targets right now, and it's in this chapter of the targets user manual. There's a built-in template that helps you get started. So if I go to our studio session, so Target Markdown, to step back, is an R Markdown interface to targets that helps prototype and construct a working pipeline, so that maybe you don't always need to directly interact with the targets file, and you can narrate how the pipeline is constructed. This is a brand new development that Christophe Derview and Yukwei were helping me out with recently. So if you install development targets from GitHub and you go to this new R Markdown, and if you create a new R Markdown document in RStudio, then you can go to From Template, and you can see that you'll have this Target Markdown template that you can create. And if you try that out, this is what you'll see. And let me just save. Oh, well, I guess it'll save when you're working on it later. But what this will allow you to do is interact with targets directly within a notebook interface. So if we load the targets package, that loads the targets engine that powers all this. Targets uses a knitter engine to power the Target Markdown interface, and you can prototype and test things. So these globals, this chunk might be something that goes into a functions.r script or a target script, but instead, when you run this target, it'll run the code and assign objects to the environment. When you go to an actual target here, instead of actually creating the target object, if you have this targets engine, what it's going to do instead is it's going to emulate the execution of a target and assign the object to the environment. So we have that object here. And likewise for collections of targets, it can emulate them, and you can have output here. And so that's interactive mode in Target Markdown. If you actually go to knit this document, it's going to run in non-interactive mode, which will actually create the files for a pipeline. And if you so choose, in later code chunks, it will run that pipeline. And so in this entire document, at no point have I needed to manually create a target script. You can see that in non-interactive mode, it'll actually write a target script and a helper script with the code in the code chunk. And because of the targets engine, which is different from the R language engine, it'll actually know to do all this. And then I have a regular R code chunk to run the pipeline. And then I have these tar read statements to process, to display output. And so you could, in theory, write an entire pipeline very easily in target markdown. And in fact, I've been doing this a whole lot at work lately for trial simulation and model validation and just modeling exercises in general. Target markdown eases a lot of the configuration and setup burden and function-oriented thinking that it usually takes to create a targets pipeline, to allow you to focus a bit more on the content of what you're doing. So that's all the material that I planned, and that's everything that I wanted to plug. These are some exciting extensions and developments to targets that take the user experience to, I think, to a new level than the early versions of targets and Drake before that was capable of. And I'd be happy to take questions now.